I now take up another important limit, and in this case let's start with a being any number which is greater than 1. So a is an arbitrary number and a is greater than 1. Now in this case, as x tends to infinity, a raised to the power x, this will tend to infinity. For example, I take up a as 1.1. So 1.1 raised to the power x, it will tend to infinity as x tends to infinity. Also, if I take up p as an arbitrary positive number, so p is greater than 0, it is an arbitrary positive number, then I see that if I go for x raised to the power p is something which is greater than 0. X raised to the power p, this will tend to infinity as x tends to infinity. For example, if I take p to be 2, so x squared, this will tend to infinity as x tends to infinity. So if I take up this case, and I take up this case, in both cases, as x tends to infinity, 1.1 raised to the power x, this tends to infinity, and here I see that as x tends to infinity, x squared tends to infinity. The point to note here is that in both cases, these numbers tend to infinity as x tends to infinity. But eventually what we are going to see here is that if I think of this case, that is 1.1 raised to the power x, this is going to increase faster than any other power of x. And I could take up 1.1 raised to the power x, or I can also think of e raised to the power x, or I can think of any other exponential function such as 1.0001 raised to the power x. So if this is the case, the point to note here is that if I have x squared by e raised to the power x, now as x tends to infinity, both of them, as in both the numerator and the denominator, will tend to infinity. But the point to note is that the denominator is going to increase at a faster rate. Eventually, the denominator will increase faster, and the denominator is the exponential function. So the point to note here is that the exponential function it increases faster than any power of x. So in this case, the denominator is going to, as x tends to infinity, both numerator and denominator will tend to infinity, but the denominator will tend to infinity at a greater pace, as in it will reach infinity, or it will get to infinity at a much greater pace than x squared. And even if I take up x raised to the power 10 divided by 1.1 raised to the power x, even here I see that both numerator and the denominator will tend to infinity as x tends to infinity. However, I have to note here that again the denominator will increase at a much faster pace, because that's nothing but my exponential function, and I know that the exponential function increases faster than any power of x. In other words, we can say that exponentials drown powers. Basically, if you have any power of x, I know that that is going to tend to infinity as x tends to infinity, but the exponential is going to drown this. What I mean to say here is that the exponential function will increase much faster than any power of x. So even in this case, the numerator and denominator, I know both tend to infinity as x tends to infinity, but the denominator will tend to infinity. It will tend towards infinity at a much faster pace. Keeping this in mind, I can say that if I have this limit x tending to infinity, x raised to the power p divided by a raised to the power x. So again here, if I take up this fraction x raised to the power p divided by a raised to the power x, I have to keep this in mind that here a is greater than 1 and p is a fixed number. It is a fixed number. In this case, again, if I just take up this fraction, I see that both numerator and denominator, they tend to infinity as x tends to infinity, but the denominator tends to infinity at a much faster pace. What does that mean? That means the fraction is going to tend towards 0 as x tends to infinity. So that means this is equal to 0. And if we want to prove this, so basically what we are trying to say here is that x raised to the power p divided by a raised to the power x, this tends to 0 as x tends to infinity. We want to prove this, and to prove this I can actually think of this diagram. So here I see that as x tends to 0, ln x tends to infinity. So if I want to think of this tending towards 0, that means if I prove that this ln of x raised to the power p divided by a raised to the power x, this should tend to minus infinity as x tends to infinity. If I prove this, then my job would be done, because of this fact that here from this diagram I can see, from this figure I can see that as x tends to 0, ln x tends to minus infinity. So that means if I want to prove that x raised to the power p divided by a raised to the power x, this tends to 0, I can actually think of ln of this tending towards minus infinity. So now let's just see, as x tends to infinity, is it the case that ln x raised to the power p divided by a raised to the power x, is it the case that this tends to minus infinity or not? For that, let me write this: ln x raised to the power p divided by a raised to the power x. This can be written as ln x raised to the power p minus ln a raised to the power x, which can then be written as p ln x minus x ln a. And this can then be written as, I can take x out, so p ln x by x minus ln a. I know that a is greater than 1. What does that mean? That means ln a is greater than 0 because I have this. Whenever I see that x is whenever I see that x is greater than 1, I see that ln x is greater than 0. If x is less than 1 and greater than 0, ln x is less than 0. But what I see here is that as x is greater than 1, ln x is greater than 0. That just means in this case, if a is greater than 1, ln a is greater than 0. So now we take a look at this. We have to prove that limit of this expression as x tends to infinity is minus infinity. In fact, I should actually prove that ln x raised to the power p divided by a raised to the power x, this should tend to minus infinity as x tends to infinity. I know that ln a is greater than 0. If somehow I prove that this expression tends to 0 as x tends to infinity, then this whole expression will tend to x minus x ln a. If ln x by x tends to 0 as x tends to infinity, then this whole expression will tend to minus x ln a as x tends to infinity, and that means this whole expression will actually tend to minus infinity because x tends to infinity, ln a is greater than 0. I already know that. That means this expression will tend to minus infinity as x tends to infinity. So somehow we have to prove that ln x by x should tend to 0 as x tends to infinity. This is what I should prove. I would like to show that ln x by x, this should tend to 0 as x tends to infinity. Because if this is the case, I'll repeat that if this is the case, that means I can then prove that p ln x by x minus ln a, then this will tend to minus ln a. And I can then say that x p ln x by x minus ln a will tend to minus x ln a. And I know that this expression, this will tend to minus infinity as x tends to infinity. So obviously that means ln x raised to the power p by a raised to the power x will tend to minus infinity as x tends to infinity. But I would like to actually prove that ln x by x should tend to 0 as x tends to infinity. Only then my proof would be complete. For that, we can actually use the L'Hopital's rule for the infinity by infinity case. So I can write that here we use the L'Hopital's rule for this case. For this case. And that means I'm actually going to prove that limit x tending to infinity ln x by x, this should turn out to be 0. So if I actually see that this will actually be the infinity by infinity case, and that means I can apply the L'Hopital's rule So I can go for limit x tending to infinity. If I differentiate ln x with respect to x, I get 1 by x. I differentiate x with respect to x, I get 1. So that means I have limit x tending to infinity 1 by x, and that gives me 0. So I have now proved that ln x by x tends to 0 as x tends to infinity, and that means p ln x by x minus ln a tends to minus ln a as x tends to infinity, and that means x multiplied by p ln x by x minus ln a, all of this tends to minus x ln a as x tends to infinity, and that means minus x ln a, this tends to minus infinity as x tends to infinity, precisely because I know that ln a is greater than 0. So now we have proved that ln x raised to the power p divided by a raised to the power x, this tends to minus infinity as x tends to infinity. And this is what we wanted. And if we have proved this, this implies x raised to the power p by a raised to the power x, this tends to 0 as x tends to infinity. And this is exactly what we had to prove, that exponentials drown powers. So you have limit x tending to infinity x raised to the power p by a raised to the power x equal to 0. Keep in mind that a is greater than 1 and p is any arbitrary positive number.